after years of planning and anticipation, the major excavation for the massive concrete shielding and foundation walls is almost over. The base of this excavation lies 45 feet below the ground level. Here, that additional excavation begins. The structural reinforcing bars form the outline of the massive base slab. With this in place, it's time to call for the concrete, which will be poured in one monolithic or continuous pour. This enormous task, once started, must not be interrupted until it's complete. Before sunrise, at approximately 4 a.m., the first truck rolls into position and the delivery pattern is set into motion. Truck after truck of concrete arrives at the job site and waits in turn to be emptied and replaced by the next full truck. The long arm of the concrete pumping machine is maneuvered by remote control from high atop the excavation site, while down below, workmen guide the steady flow of concrete. Through the day and into the evening, the job goes on until 8:30 p.m. when the last load of concrete is delivered. The slab has been finished in 17½ hours. The rebar rising from the base slab outlines the sidewalls for the gantry pit. As the huge forms are lifted into place and the sidewalls are nearly completed, the gantry pit area is clearly defined. Here, the gantry pit floor slabs are finished and sloped to floor drains. As additional forming of the upper gantry walls is underway, the backfilling operation begins in the areas next to the gantry pit walls. Once this is done, level B floor slabs can be poured. Structural steel framing outlines the shape of the building, and the seemingly endless task of forming the concrete shielding walls continues. The footprint of the structure is more visible from this overhead view, which emphasizes the entire plan of the proton therapy facility. Steel is placed on structural concrete decks atop each of the 3 gantry rooms, the fixed beam room, and also the calibration room. The steel arrives in large sections and is layered in a pattern of overlapping joints. The steel will later be covered and encased with additional concrete. This will form a thick, sandwich-like barrier, which will be the radiation shielding for the hospital structure to be built above. Work goes on in areas adjacent to the heavy shielding walls as layer after layer of the steel continues to be set. This is part of the 36-inch thick steel that will be over each gantry structure. The rebar walls around the steel piles indicate how thick or deep the concrete cap will be. Even though the steel is in very large sections, each piece must be placed in a specified location and fitted as closely as possible. Lead shot is poured into the cracks to eliminate the possibility of radiation leaks. The concrete cap over the gantry steel shielding is now poured in place, and the formwork of level 1 can be laid. With the concrete for the gantry area complete, the pouring of the adjacent level 1 slabs can begin. Here, level 1 is almost complete. Finishing this slab will totally enclose the proton therapy facility, which is 45 feet below this slab. Imagine a sidewalk, 4 feet wide, running from Loma Linda to Los Angeles, about 45 miles, and you will have an idea of how much concrete was used for this phase of construction. That's 14,200 cubic yards of cement. And let's not forget the 800 tons of shielding steel required. That would equal the amount of steel it takes to make over 500 automobiles. This phase of construction was completed on April 6, 1989, which is just 1 year minus a day from when the groundbreaking ceremonies were held April 7, 1988. The excavation of the building began on August 5, 1988, and this massive substructure was completed in 8 months. The next step involves preparing the inside for the tedious task of installing the proton therapy treatment equipment. Soon, these unfinished corridors, which lead to empty rooms, will house the dramatic new tool for the treatment of cancer. Let's take a look inside, where workmen are finishing portions of the gantry room and gantry pit areas. From this view on level B, we can see the embedded plates for the seismic and axial supports of the gantry cone. highly sensitive survey instruments are required for the setting of embedded monuments at critical locations throughout the entire proton therapy facility. The proton beam, traveling from the accelerator to the gantry rooms, or the fixed beam room, must have 10,000ths of an inch tolerance. The magnets which control the beam must also be precisely located and surveyed into position within this same tolerance. When the beam enters the gantry room and is transported through the magnets on the gantry to the ISO center, the beam must be within a tolerance of less than 1 millimeter. Each of these rings must be within 2 mils tolerance for both concentricity and circularity. Each ring weighs approximately 15,000 pounds and is turned on a horizontal lathe to ensure that this tolerance is met. As other portions of the structure are added, the assembled gantry cone is machined and remachined to ensure that the strict tolerances are always maintained. As the blueprint plan becomes reality, the project reflects the pride and enthusiasm of each worker. From the manufacturers to the construction crew, we see a unity of purpose and dedication that is almost tangible. At the plant, the completed cone section is being lowered on its matching pedestal roller assembly to make sure the ring matches perfectly and can rotate within the design tolerances. The 9,000-pound truss sections for each of the 3 gantry structures are fitted to the cone section and remachined if necessary to ensure perfect fit and alignment. After each gantry structure is completed and fitted, it will be taken apart for shipment. Each one will then need to be reassembled and installed in its own gantry room chamber. On June 14, 1989, the rings for the first gantry arrive at Loma Linda. Guided by experienced hands, the first ring is slowly lowered to level A. From level A, the ring must be lowered inch by inch to the gantry pit 35 feet below. The chore of reassembling this 60-ton structure now begins. Constant alignment procedures are met with each stage of the reassembly. The 36 by 36 by 12-foot wide gantry chamber will soon be filled with an instrument that can allow the proton beam to be delivered to a cancer tumor from almost any direction or angle as the patient lies comfortably in one position. During the year of construction at Loma Linda, the accelerator was being tested and commissioned at Batavia, Illinois, home of the Fermi National Accelerator Laboratory. After passing all the strict performance tests, the accelerator is taken apart. All the components, as well as every cable and wire, must be systematically labeled to ensure a smooth reassembly. Once this is accomplished, the accelerator is carefully packed in the custom crate designed for shipping to California. Back in Loma Linda, the beam transport system is receiving the final touches necessary prior to the arrival of the accelerator and components. Here, the support stands for the beam transport system components are being secured. The magnets that will steer the proton beam from the accelerator to the treatment rooms are also being placed. Electronic support equipment with miles of control and power cables are methodically installed. Progress is now visible as the moving vans arrive with the first load of accelerator components and support equipment. With thousands of pounds of cargo involved, it will take about 8 truckloads to bring all of the equipment from Illinois. As the trucks are unloaded, the equipment is lowered into the building where it will be permanently installed. The accelerator component stands are precisely located and anchored into place. These stands were designed not only to support specific components, but to withstand earth vibrations. Some of the injection line components that were supported from the floor at Fermilab will be suspended from the ceiling to allow access to the equipment that lies beneath the injection line. With the accelerator components in place, the final precision adjustments begin. The entire beam delivery system must be aligned to a tolerance of 10,000ths of an inch or better. To power the accelerator and all of the beam transport components, custom-designed power supplies are installed along the entire beam transport system. The larger magnets, such as the bending dipoles and switching dipoles, are powered by 3,000 amp power supplies that are water-cooled. The smaller trim magnets and quadrupoles are operated by much smaller power supplies. As with any room full of powerful electrical equipment, heat will be generated. There are 2 water plants, or skids, designed to cool and service the entire beam transport system. The magnets are the conventional water-cooled design. One skid will furnish deionized water to the accelerator components and the larger power supplies only. The other water skid, which is located in the main switchyard, will serve the rest of the beam transport system, the magnet components, and the gantry magnets.